All right, let's dive right in. If you're prepping for an exam or just need a solid, quick refresher on the cardiac cycle, then you've come to the right place. We are going to break down every single event in one heartbeat, and these slides are going to make sure it all clicks into place for you. So here's our game plan. First, we'll cover the basics of the heart as two pumps working side by side. Then we'll look at the valves, the heart's own little gatekeepers. After that, we'll get into the electrical signal that starts the whole show, then walk step by step through one complete heartbeat. And finally, we'll put it all together in one big summary view.
Okay, first things first. We have to start with the most fundamental idea. It's really easy to think of the heart as just one big pump, but it's so important to remember that it's actually two separate pumps fused together working in perfect sync.
And this image shows those two circuits perfectly. On one side, you've got the pulmonary circuit. That's the right side of the heart, pumping that oxygen-poor blood, the blue stuff, on a quick trip over to the lungs to get reoxygenated. Then, that fresh, oxygen-rich blood, now shown in red, comes back to the left side of the heart, which powers the much bigger systemic circuit, pushing blood out to literally every other part of your body.
This right here really drives home the difference in their jobs. Think about it. The right heart just has to push blood next door to the lungs. It's a low-pressure gig. But the left heart, it has to generate some serious force to get blood all the way up to your brain and down to your toes. That's why it's a high-pressure system, and that's exactly why the muscle wall of the left ventricle is so much thicker.
So, we have these two pumps pushing blood around. But how does the blood know not to flow backward? Well, that's where our gatekeepers come in. We've got 4 heart valves, and their entire job is to make sure blood flow is a one-way street.
And here you can see one of those atrioventricular, or AV valves in action. Look at the diagrams up top. On the left, pressure from the atrium is higher, so it pushes the valve flaps open, letting blood pour into the ventricle. But look at the right. The second the ventricle starts to squeeze, that pressure reverses. It pushes up on the flaps and snaps the valve shut, making sure no blood can leak back into the atrium.
The main takeaway here is really simple. It's all about pressure. It's a beautifully simple passive system. Pressure from behind pushes the valve open. The moment that pressure reverses, the blood trying to flow backward is actually what fills up the little flaps and slams the door shut. No muscles or nerves needed for the valve itself to work.
Okay, so we've covered the plumbing and the one-way doors, but what actually tells the pump to, well, pump? That would be the electrical system. The heart has this amazing property called autorhythmicity, which basically means it generates its own electrical spark, its own rhythm, to create the heartbeat.
This diagram shows us exactly how that electrical signal, which we can see on an ECG, lines up with the physical squeezing of the heart. So let's follow it. It all kicks off with the P wave, that first small bump. This represents the electrical signal, or depolarization, spreading across the atria. And that signal is the direct trigger for the atria to contract.
Next up, you see that big, sharp spike? That's the QRS complex. Why is it so much bigger than the P wave? Well, it's because it represents that same electrical signal spreading through the much thicker, much more muscular ventricular walls. This triggers their much more powerful contraction.
And finally, we get the T wave. You could think of this as the electrical reset signal. It's called repolarization, and it's what tells the ventricles, okay, job done, time to relax, so they can refill for the next beat. So P, QRS, T. Atria squeeze, ventricles relax. That's the pattern.
All right, now for the main event. Let's put everything together. We're going to connect the electrical sparks, the pressure changes, the valve movements, the whole shebang, to walk through the entire 0.8-second journey of a single heartbeat.
Now, this is our master diagram. I know it can look a little intimidating at first glance, but trust me, it's amazing. It lays out how everything, the ECG, the pressures, the volume, even the heart sounds, all line up perfectly. We're just going to break it down phase by phase. So, let's start at the very end of the filling phase. The atria have just given that final little squeeze to top off the ventricles. At this exact moment, the ventricles are as full as they are going to get. This maximum volume, around 130 milliliters at rest, has a special name, the end diastolic volume, or EDV. This is our starting line for contraction.
Now, you gotta pay close attention right here, because this part's crucial. The instant the ventricles start to squeeze, the pressure inside slams the AV valve shut, but the pressure isn't high enough yet to push the exit valves open. So for a split second, all 4 valves are closed. The muscles contracting like crazy, pressure is skyrocketing, but the volume of blood inside isn't changing. That's isovolumetric contraction.
So have you ever actually wondered what makes that classic lub-dub sound of a heartbeat?
It's not the muscle squeezing, it's the sound of the valves slamming shut. That first heart sound, S1, the lub, is the sound of those AV valves closing right at the start of isovolumetric contraction.
So, once the pressure inside those squeezing ventricles finally builds up enough to overcome the pressure in the aorta, which is about 80 millimeters of mercury, the semilunar or exit valves are just blown open. This is the big moment, ventricular ejection, where blood is powerfully launched out of the heart into both the pulmonary and systemic circuits. Then after all that work, the ventricles start to relax and the pressure inside just plummets. The back pressure from the aorta and pulmonary artery immediately snaps the semilunar valves shut, and that creates the second heart sound, S2, the dup. And just like before, for a brief moment, all 4 valves are closed again while the ventricle relaxes. This is isovolumetric relaxation.
Whew! Okay, that was a lot of moving parts, I know. So let's wrap this up by putting it all together into one single, clean summary. This is going to be perfect for studying and for a quick review before a test.
This table is pretty much your best friend. It connects every single thing we just talked about. You can see how each phase lines up perfectly. Ventricular filling, AV valves are open, and it ends with the P wave. Isovolumetric contraction, all valves are closed, and it's kicked off by the QRS complex. Ventricular injection, the semilunar valves are open. And finally, isovolumetric relaxation, all valves closed again as the ventricle resets during the T wave. It's the entire story, all in one place.
So let's end with a question to get you thinking. We know afterload is the pressure in the aorta that the ventricle has to fight against to open that valve. So think about this. How would chronic high blood pressure, which is just a constant state of increased afterload, affect the timing of ventricular ejection? Working through that is really going to lock in your understanding of how all these pressure dynamics work in the real world.